So, what controllability actually says is that starting with some x naught value, okay. Let us take the previous example. Okay, let us not worry about the output part. Okay. This is kind of, the previous example is kind of related to the example that I talked about, stirred tank heater. Let us say our stirred tank heater, our x1 was height, our x2 was temperature, our input was the heater. Okay. So, you will have we very briefly did this linearization in module 3, and we said okay, height affects itself. So, we will have this minus alpha over here. Okay. Temperature does not affect the height. So, we have 0 over here. Okay. Height affects temperature. So, we will have some beta over here, and temperature itself affects temperature. So, we have this again negative alpha over here. Okay. And when we talked about the heater power does not affect the height. So, we had this as 0 and this as some gamma. Okay. Alpha, beta, gamma are just numbers. Okay. You can fill them up with whatever you want, and the analysis really will not change. Okay. The first thing that is there is that these maybe I will not put this negative, let us just keep it alpha and beta. Okay. So, the first thing that is there is that the way that system is, okay, it's alpha and alpha are the eigenvalues. Okay. They come from the physics behind this, and these eigenvalues in the example that we talked about yesterday, there were two cases we said. One was the outlet flow rate depends on height. If the outlet flow rate depends on height, the values of alpha are definitely going to be less than 1. Okay. That is how it kind of works out. It works out because it is 1 divided by 1 plus something, 1 plus a positive number. So, this alpha is guaranteed to be less than 1. Okay. If it does not depend on height, the outlet flow rate does not depend on height, then one of the alphas is going to be 0. So, and therefore, you will lose that controllability. So, that will not be alpha alpha, it will be alpha 1 alpha 2. Okay. That is the background behind how those values come. Do not worry about the background, I am just trying to relate the physical example with the matrices that we obtain. Okay. So, now what we are trying to say is, can we determine U's in the future such that we reach from an arbitrary initial state, we reach any kind of desired state. Okay. So, let us say we start with x naught, okay, and let us say at time k equal to 0, we implement u naught. okay, then x1 is going to be alpha 0 so which is equal to gamma u naught, okay. x2 is going to be alpha 0 beta alpha so okay, this part I have just called it as A, okay. So you will get alpha square x1 naught and then you will get alpha beta x1 naught plus alpha A plus gamma u1 for example, okay. If you see what is happening over here is your u1 is not affecting your the first element of your state. If you look at this, your u0 and u1 are affecting that state. So you can choose u0 if you were to choose u0 equal to negative a by gamma. Immediately at time k equal to 1 you have reached 0 in your x2, but your x1 will completely evolve on its own, okay. You have no way in order to affect x1. So this system is not reachable, you cannot take it to any arbitrary xf. This is not even controllable because it will reach origin only at infinite time, because alpha square alpha to the power n multiplied by x1 naught is going to be 0 only as n tends to infinity if your alpha is less than 1. If your alpha is greater than 1, the system is not even stabilizable, okay. So system which is given by now this was a little bit easy to see, right. Why? Because you could actually see that input does not affect x1, okay, and x2 does not affect x1. How can input affect any state? Input can affect a state by directly affecting that state or indirectly affecting that state. So it can affect the state by affecting directly. So let us say if this was say 0.1, okay, then input will first affect x2, in the next time step x2 will start affecting x1, okay, but if it is 0 then that also is not going to happen. So this was an obvious case, but let us consider a less obvious case. let us say A was equal to, or let us put it this way. So, let us do it in this way. The question is whether or not this system is controllable. Okay. So, the way we look at controllability is we will write x1 equal to Ax naught we did that yesterday. Okay, you keep multiplying, I mean you keep substituting the value of xk in the equation Axk plus xk plus 1 equal to Axk plus Buk. That way you will get a to the power k x naught plus a to the power k minus 1 . If you put all of this together, okay, this is what you get. Okay. So, first question is the system stabilizable? Okay. If eigenvalues of A are all lying in unit disk, which means if the system is asymptotically stable, the system is stabilizable. You do not even have to do anything else, do not have to worry about it. So, any stable system is stabilizable. If a system is not stable, then it is stabilizable only if the unstable components of that systems are reachable. We will talk about that in a bit. Okay. The question is the system reachable? The system is reachable if and only if this particular guy is invertible. Why is that so? Is if you take look at this, you will get xk minus a to the power k x naught, that is going to be equal to this multiplied by u naught. Okay. Can you find set of u naughts so that you can go to any arbitrary xf? When can you find that set of u naught? When the left inverse exists. Okay. So, if you look at this, you can write this as, let us say at time k you have to reach some final point xf. So, xf minus we will call this as wc. Okay. A solution is possible to this only if wc is invertible. So, the controllability condition sorry, as a left inverse. So, controllability condition is rank WC equal to N, okay. But you do not have to take the WC to a very large value of K, you only have to take WC to equal to K equal to N. Why? Because of the Cayley-Hamilton theorem, okay. What does Cayley-Hamilton theorem say? That a to the power n is linearly dependent on a to the power n minus 1, a to the power n minus 2 up to a to the power 0, okay. So, any higher powers of a are linearly dependent on lower powers of a, and therefore, you only need to check the WC matrix up to a to the power n minus 1 multiplied by b, okay. This is one result. Another result is called Haugh's condition, okay. Okay. So, when you construct a matrix like this, so A minus lambda 1 followed by B, so you are just concatenating them, okay. If you construct this, so there are going to be n such matrices for each of these eigenvalues, okay. What happens when you do something like this? The matrix loses its rank, right, because this at least has one dimensional null space. We have talked about that in our first module, okay. So, if okay, so that is what you actually get, okay. If rank of, I do not write this down, I will erase, okay. If rank of Mi is equal to n, if Mi has a full rank, okay, then the subspace corresponding to that is reachable, okay. So, for the entire system to be reachable, what is the criteria? The criteria is that rank of all such MIs should be equal to n, okay. So, the Haugh's condition is going to be both of these are equivalent conditions. What does that mean? Let us say A or let us say the system is stable. What does that mean? All lambda i's lie in unit disk, Okay. Then because all lambda i's are lying in unit disk, there is no lambda I which is greater than 1. Okay. So you do not even have to worry about rank of mi's, right. Okay. So what does stabilizability condition mean? Stabilizability condition means that only for those lambdas which are greater than 1, A minus lambda I B should have full rank, then stabilizability is guaranteed. What does reachability mean? For all lambda i's, A minus lambda I followed by B should have a full rank. Okay. So these are the two conditions. The third item that we have okay, if all sigmas okay. So this is what this means. Okay. If you do SVD on WC, if the system is reachable, all the singular values will be positive. If the system is non-reachable, okay, let us say only one singular value is positive, you will have one dimensional unreachable subspace. That unreachable subspace is going to be the subspace spanned by the last of the u vectors. If you have two dimensional subspace which is unreachable, the last two will be such in such a way. Okay. So with that I finished the class. So if anyone wants to leave, they can leave. What we will do in the next class? We will take two examples. Example 1 is same as before, alpha 0, beta alpha 0, gamma. And then apply all those three conditions. The case 2 we will take is 2 0 1 1 1 1. Okay. So if you see your WC, which is AB followed by B, can immediately see this is 0 alpha gamma 0 gamma, rank is 1. Okay. So the system is unreachable. Okay. The system like this, you will see this is AB B, which is going to be equal to 2 2 1 1. Again rank is 1, it is unreachable. Okay. You will see that the reachable subspace is 1 1, unreachable subspace is 1 minus 1. We have done that in module 1. You will not immediately get it, we will solve this problem, but this is what we will do in the next class, okay, and then we will see if we can finish off the next condition called observability, okay. So, for this class, to summarize, controllability condition, you build the WC is called controllability Gramian. Okay. So, full rank WC matrix means the system is controllable. Then you have this Hautus condition where you check whether or not the rank of A minus lambda I comma B is equal to n. Okay. And the third thing is SVD on WC will tell you which subspaces are reachable and unreachable. Okay.